39 seconds. That's the whole story, and it's the part almost no one understands yet. On the night of June 24th, the ground under northern Venezuela moved twice. The first time, it was a magnitude 7.2. People barely had time to register that something was wrong. 39 seconds later, before the first wave of shaking had even finished, the earth hit them again. A magnitude 7.5. Two of the largest earthquakes this country has felt in more than a century, stacked back to back, in less time than it takes you to read this sentence out loud. And here's the strange thing, the part of that night that did the most killing wasn't the shaking. I want you to hold on to that, because it runs against every instinct you have. When we picture an earthquake, we picture buildings shaking apart. We picture the violence. But in Caracas, and in the coastal strip below it, the strongest shaking on the map is not where the worst collapses happened. Something else was waiting under the ground. Something that turns solid earth into something closer to liquid in a matter of seconds. And by the time we're done, you'll understand exactly what it was, why it targeted the tallest buildings first, and why it is still a threat right now, tonight, to a coastline where more than 170,000 people are still standing on it. You'll also understand something the headlines got wrong. You'll know why two different teams of scientists are still arguing about what actually ruptured that night. You'll know why a tsunami warning went out to United States soil, to Puerto Rico and the Virgin Islands, within minutes. And you'll know what the United States Geological Survey is now forecasting for the next several days, because the sequence that started on June 24th is not finished. This is the Horizon Lab. We don't do conspiracy here. We do the verified version, with the real data on screen, because the truth about what happened in Venezuela is more unsettling than any theory you'll find in your feed. So before we get into it, if you want the science behind the disasters that everyone else only sensationalizes, subscribe. It genuinely helps this channel reach more people who want the real story. And tell me in the comments where you're watching from, because by the end of this, you may look at the ground under your own city a little differently. Let's get into it. 2 quakes, 39 seconds. A coastline that even now has not stopped moving. Let's start with what the instruments actually recorded, because the precision here matters. At 22:04 and 33 seconds Coordinated Universal Time on June 24th, the United States Geological Survey logged the first event. A magnitude 7.2. The epicenter sat about 23 kilometers southeast of the town of Altamira in northern Venezuela, at a depth of roughly 20 kilometers. On its own, that quake would have been the lead story on every newscast in the hemisphere. A 7.2 is a major earthquake by any definition. It releases more energy than the bomb dropped on Hiroshima, many times over. But it wasn't on its own. 39 seconds later, at 22:05 and 11 seconds, the ground ruptured again. This time, a magnitude 7.5, centered about 28 kilometers southeast of the same town, but shallower. Only about 10 kilometers down, and that depth is not a small detail. A shallow quake delivers more of its energy straight up, into the surface, into the buildings and the people standing on it. The second quake was bigger, and it was closer to the surface, and it arrived before the first one had finished rolling through the region. Seismologists have a word for this. They call it a doublet. 2 large earthquakes, very close together in time and space, similar in size, where the first is not simply a foreshock to the second, and the second is not simply an aftershock of the first. They are something more like equal partners. And doublets are rare. Most large earthquakes are followed by aftershocks that are noticeably smaller. A true doublet, 2 near equals separated by less than a minute, is the kind of event seismologists study for years. Now think about what that means for a person standing in a stairwell in Caracas that night. You feel the floor lurch. Your body does what every human body does. It freezes. It tries to understand. It reaches for a doorway. The experts will tell you that you have, at most, a few seconds of useful warning before the strong shaking arrives. In a normal earthquake, that's the moment you act. Drop, cover, hold on. But in Venezuela that night, just as the first quake's shaking was peaking, just as people were reacting to the first blow, the second blow landed. Larger, shallower. There was no pause to think, no window to get out. The ground simply did not stop. That is the first reason this event was so deadly. It compressed two disasters into one breath. And it's also the first place where the official record gets complicated, because not every scientist agrees that what I just described is even the right way to count it. Hold that thought. We'll come back to it, and it will tell you something important about how honest science actually works. Here's a question worth asking before we go any further. Why should someone watching this in Ohio, or Texas, or California care about an earthquake in Venezuela? There are three answers, and the first one happened within minutes of the second quake. A tsunami advisory went out for United States soil, Puerto Rico, the United States Virgin Islands, the British Virgin Islands, the so-called ABC Islands off the Venezuelan coast. The Pacific Tsunami Warning Center, which also covers the Caribbean, looked at a shallow magnitude 7.5 on a coastal fault and did exactly what it is built to do. It warned people. For a few hours that night, Americans on Caribbean islands were checking the water, moving away from the shore, waiting to find out whether the sea was about to come for them. The advisory was eventually cancelled at 12 minutes past 7 in the evening, Atlantic Standard Time. But for those hours, this was not a foreign story. It was a domestic one. That's the first reason. The second is geography. The fault that ruptured is part of a system called the San Sebastián fault, and that system runs right along the northern edge of Venezuela, parallel to the coast, which is where most of the country's people live. The capital, Caracas, sits just inland from it. The port of La Guaira sits right on it. Maiquetía, where the international airport is, sits on it. This is not a fault out in some empty stretch of ocean. This is a fault threaded directly underneath one of the most densely populated coastlines in South America. And that's the part I want you to make personal. Picture a major strike-slip fault, the same kind of fault, running just offshore of a crowded American coastal city. A city built on soft coastal ground, with high-rise towers, an international airport, a major port, all packed into a narrow strip between the mountains and the sea. If that sounds familiar, it should, because that is a fair description of more than one place in the United States. The specific names are different, the physics are identical. The third reason is the simplest: people. American search and rescue teams, American naval ships, American money, all of it moving toward Venezuela within days. We'll get to exactly who showed up and what they brought, because that part of the story tells you something about how the modern world responds when a city goes down. But understand this from the start. The line between a foreign disaster and a domestic one is thinner than we like to pretend. A fault does not check passports. The same kind of ground that failed in La Guaira exists under American cities too. So when I say this is your coast too, I'm not reaching for drama. I'm describing a fault system, a population density, and a type of soil that you can find, in different combinations, much closer to home. Now let's talk about why one earthquake can pull the trigger on a second one in less time than a held breath. To understand the 39 seconds, you have to understand what a fault actually is, and most of what people picture is wrong. A fault is not a single crack in the ground like a line drawn on a map. It's a vast, rough surface, buried in rock, where two enormous blocks of the Earth's crust grind past each other. In Venezuela's case, the motion is mostly side to side. Geologists call that a strike-slip fault. The Caribbean plate and the South American plate are sliding past one another, roughly an inch or two a year, and the San Sebastián system is one of the seams where that sliding happens. An inch a year sounds harmless. It isn't, because the two blocks don't slide smoothly. They lock. Friction holds them in place, year after year, decade after decade, while the deeper plates keep pushing. The rock bends. It stores the strain like a drawn bow, and it waits. When the friction finally loses, the stored strain releases all at once. That release is the earthquake. The longer the lock held, the more energy comes out. Now, here's the mechanism behind the doublet. When one section of a fault ruptures, it doesn't just release its own strain, it shoves the rock around it. Imagine a long row of bricks all leaning against each other under pressure. Pull one out, and the load it was carrying doesn't vanish. It transfers to the bricks on either side. Suddenly they're carrying more than before. Scientists call this stress transfer, and it's one of the most important ideas in modern seismology. When a fault breaks, it can pile extra stress onto a neighboring section that was already close to failing. Sometimes that neighboring section holds for weeks, and we call the eventual break an aftershock. Sometimes it holds for years, and sometimes, when a fault is loaded just right, it holds for less than a minute. That appears to be what happened in Venezuela. The first rupture, the magnitude 7.2, transferred its load almost instantly onto an adjacent stretch of fault that was already at its breaking point. 39 seconds was all that section could take. Then it went too. Think of it like a crack racing across a frozen lake. The ice breaks under your feet, and you watch the fracture shoot outward, splitting more ice as it goes, faster than you can react. The energy from the first break is what drives the second. The fault didn't pause to consider. The physics simply played out. And this is why the timing was so lethal. In a normal large earthquake, the worst shaking lasts maybe 30 to 60 seconds, and then it eases, and survival often comes down to what you do in the moments right after. But a doublet erases those moments. The recovery window between the two blows was gone before anyone could use it. The ground gave people no time to run, no time to pull someone out, no time to get clear of a leaning wall. It just kept going. So that's the trigger, and that's the timing. Two ruptures, one driving the other, in less than a minute. But the size of the quake and the speed of the quake still don't fully explain what happened next, because the deadliest force that night wasn't released by the fault at all. It was released by the ground itself. And to understand that, we have to talk about what the official agencies actually saw when they looked at the wreckage, and why two respected teams of scientists still can't agree on what they were looking at. Here's something the headlines didn't tell you. The scientists don't fully agree on what happened that night. I don't mean the conspiracy crowd, I mean the actual agencies, the people whose entire job is to measure earthquakes with instruments. They are looking at the same data, the same seismic waves recorded by stations around the world, and they are reaching different conclusions about what physically ruptured under Venezuela. And I want to walk you through that disagreement, because it is the opposite of a weakness. It is how real science works, out in the open, in real time. The United States Geological Survey reads the event the way I've described it to you. Two distinct earthquakes, a magnitude 7.2, then a magnitude 7.5, 39 seconds apart, on the San Sebastián fault system. Their finite fault modeling, which is the process of reconstructing how the rupture spread across the fault surface, points to a combined rupture stretching well over 200 kilometers in length, with the slip on the fault reaching around 2 meters in places, and the whole thing playing out over more than 90 seconds. But another respected group, the GEOSCOPE network, modeled it differently. Their analysis suggests it may have been better understood as a single, complex event, one larger earthquake, closer to a magnitude 7.8, that ruptured in a complicated, multi-stage way, rather than as two clean, separate shocks. Now, why does this matter to you sitting at home? Two reasons. The first is simple honesty. When you see a single magnitude number flashed on a news graphic, it looks like a fact carved in stone. It usually isn't. Magnitude is a calculated estimate, refined over hours and days as more data comes in, and on a messy, fast, overlapping event like this one, even world-class teams using world-class instruments can land in different places. Anyone who tells you they know the exact, final, certain answer about what ruptured that night, less than a week later, is selling you something. The second reason is more interesting. The difference between two separate sevens and one complex 7.8 changes how we understand the fault itself. If it was a doublet, then two adjacent sections failed in sequence, and the stress transfer story I told you a moment ago is the right frame. If it was one complex rupture, then a single, much longer stretch of fault let go in one coordinated event, which tells us something different and frankly more alarming about how much of that fault system was loaded and ready. Either way, the energy released was immense. Either way, a huge length of fault moved. The debate is about the choreography, not about whether the dance was deadly. This is the part conspiracy channels can never give you, because admitting uncertainty doesn't sell fear as cleanly. But the real picture is this. Serious scientists are still working it out, the numbers will keep getting refined, and the honest answer right now is that it was either two enormous quakes or one even larger one. Hold both possibilities in your head. That's what the data actually supports. And whichever it was, it set the stage for the thing that did the most damage. Not the magnitude, not the choreography, the ground. This is the heart of it. So let me slow all the way down. When the United States Geological Survey assesses an earthquake, it doesn't just publish a magnitude. It publishes something called a shake map, which shows how violently the ground actually moved in each location, and it publishes a separate set of alerts for ground failure. And when you look at the ground failure assessment for Venezuela, you find something that should stop you cold. The shaking itself was extreme. The shake map recorded peak intensities up to the level scientists call violent, the second highest category there is, with ground accelerations that exceeded 2/3 of the force of gravity in the hardest hit zones. That alone tears buildings apart. But the agency also issued a separate alert, and this one was coded red, the highest level. And it wasn't for the shaking, it was for liquefaction. Liquefaction, remember that word, because it's the real villain of this story. The red liquefaction alert covered an area where roughly 170,000 people live. That's the coastal strip running through La Guaira, Maiquetía, and into Caracas itself. By comparison, the landslide alert, the thing most people would expect in mountainous terrain, was only coded orange and covered a far smaller population. In other words, the single greatest ground hazard from this earthquake, according to the agency whose job is to know, was not the mountainsides coming down. It was the ground beneath the city turning to liquid. And here's the proof, written in concrete and steel. In Caracas, a 22-story tower in the Altamira district came down. Not damaged, down. And in the Los Palos Grandes neighborhood, a residential building called the Petunia Residences pancaked. 14 floors collapsed into rubble, while a handful of lower floors somehow held. These were not flimsy structures, these were modern high-rises, the kind of buildings that are supposed to ride out an earthquake. So why did they fail when other buildings nearby, sometimes older and shorter, stayed standing? The answer is the soil they were built on. Those towers were sitting on soft, water-saturated coastal sediment, and when violent shaking hits that specific kind of ground, the ground stops behaving like a solid. For a few terrible seconds, it behaves like a liquid. A heavy tower standing on solid rock will shake, but it stays anchored. A heavy tower standing on ground that suddenly turns to liquid has nothing to stand on. It tilts, it sinks, it topples. The taller and heavier the building, the worse it is, because all that weight is concentrated on a foundation that has, for a moment, simply ceased to be solid. That's why the strongest shaking on the map isn't a perfect match for the worst collapses. The collapses followed the soil. They followed the liquefaction. The earthquake pulled the trigger, but the ground is what fired the shot. Now let me show you exactly how solid earth turns to liquid. Because once you see the mechanism, you'll never look at a coastline the same way again. You've probably walked on liquefaction without ever knowing it had a name. Go to a beach. Find the wet sand near the waterline, the kind that feels firm and solid when you stand still on it. Now stay in one spot and wiggle your feet, fast, again and again. Within seconds, the sand around your feet loses its firmness. It goes soupy. Water rises up around your soles, and you start to sink. You didn't add any water. You didn't dig. All you did was shake the sand, and the shaking changed it from something solid into something that behaves like a thick liquid. That, scaled up to the size of a city, is what happened in La Guaira. Here's the physics underneath it. That coastal soil isn't pure rock. It's loose grains of sand and sediment, piled up over thousands of years, with water filling the tiny spaces between the grains. When everything is calm, the grains rest against each other, grain on grain, and all that grain-to-grain contact is what makes the ground feel solid. It can hold the weight of a building because the grains are pressing on each other and transferring that load down into the earth. Now shake it, violently, many times a second. The shaking knocks the grains loose from each other, and they try to settle into a tighter arrangement. But the water trapped between them can't escape fast enough. So instead of the grains carrying the load, the trapped water suddenly has to carry it. The pressure in that water spikes, and water cannot support a building. The instant the water is bearing the weight instead of the grains, the soil loses its strength entirely. It flows. It behaves like a liquid. Scientists call the trigger pore water pressure, but you can just picture the grains briefly floating apart, suspended in their own trapped water, unable to hold anything up. This is why tall buildings are punished worst. A heavy high-rise concentrates an enormous load onto its foundation. As long as the ground is solid, that's fine. But the moment the soil liquefies, that concentrated weight has nothing beneath it but a few seconds of soupy, pressurized ground. The building tilts as the liquefied soil squeezes out from under one side. It sinks. In the worst cases, it goes over completely, or it pancakes as the lower structure punches down into the failed earth. Meanwhile, a lighter, lower building right next door might survive, because it never put enough pressure on the ground to matter. And here's the part that should genuinely unsettle you. Liquefaction-prone ground is not rare. It is exactly the kind of soft, wet, sandy soil you find along coastlines, in river valleys, on filled-in land near harbors. In other words, it sits under some of the most desirable, most heavily built, most expensive real estate on Earth, including in the United States. Parts of the San Francisco Bay Area sit on it. So do stretches of coastal land in the Pacific Northwest, and filled ground in more than one major American port city. Engineers know this. They build for it where they can. But the soil under Venezuela's coast is the same physics that sits under a lot of places much closer to home. The earthquake was the spark, the liquefaction was the fuel, and the human cost of those two things meeting is what we have to look at next, because the numbers coming out of Venezuela are still climbing. I want to handle this part carefully, because behind every number here is a person, and the numbers are still changing as I record this. In the first hours after the quakes, the official toll was relatively low, a few hundred dead. That's normal in a disaster of this scale, not because the damage is small, but because information moves slowly through a collapsed city. Communications go down, roads are blocked, whole neighborhoods are unreachable. The early count is never the real count. It is only what has been confirmed so far. By June 27th, 3 days after the quakes, the picture had darkened dramatically. Venezuelan officials reported the death toll had risen to at least 1,430 people, more than 3,200 injured, over 3,000 families left without a home, and a number that is harder to even absorb. As many as 68,900 people reported missing by their families. Now, I want to be honest about that missing figure, because it does not mean 68,000 confirmed dead. In the chaos after a disaster, families report anyone they cannot reach. Many of those people are alive, displaced, cut off, sheltering somewhere without a working phone, but some of them are under the rubble. The grim work of the following days is the work of sorting one group from the other. And that work runs against a clock. There's a window after an earthquake, usually cited as the first 48 to 72 hours, when people trapped in collapsed buildings have the best chance of being pulled out alive. After that, the survival odds fall steeply. As I record this, that window is closing. Rescue crews are still digging, still calling into the gaps in the concrete, still listening for a response. Some are still finding people. Most, by now, are finding what the earthquake left behind. The United States Geological Survey runs a model that tries to estimate, in the very first minutes, how bad a quake is likely to be based on the population exposed to the shaking. For this event, that model flagged a real probability of a death toll exceeding 100,000 people. I want to be clear that this is a probabilistic estimate, not a prediction, and the actual confirmed toll is, mercifully, far lower than that worst case. But the fact that the model put that number on the table at all tells you the scale of what could have happened, and the scale of what still might, if the sequence isn't over. Here's what I won't do. I won't put a made-up face on this for you. I'm not going to invent a survivor and feed you a quote they never said, the way a lot of channels do to manufacture emotion. The real detail is heavy enough. 1,430 confirmed dead, and climbing. 68,000 reported missing. 3,000 families who went to sleep on June 23rd in their own homes and no longer have one. Those are not characters. Those are the verified figures from officials on the ground, and they are still moving in the wrong direction. And the reason they may keep moving brings us to the part of this story that is not history at all. It's a forecast. Because the United States Geological Survey is now telling us, in plain numbers, what the odds are that the ground under Venezuela breaks again in the days ahead. We'll get to that forecast and to the tsunami warning that reached American shores right after this. Within minutes of the second quake, an alert went out that turned this from a Venezuelan disaster into an American one, at least for a few tense hours. The Pacific Tsunami Warning Center issued a tsunami advisory, and despite the name, that center doesn't just watch the Pacific. It covers the Caribbean too. The advisory reached Puerto Rico. It reached the United States Virgin Islands. It reached the British Virgin Islands and the string of islands off the Venezuelan coast. For people on those islands, the message was immediate and physical. Get away from the water, move off the beaches, stay out of harbors and marinas. The sea might be about to do something dangerous. Now, you might be wondering why a side-to-side, strike-slip earthquake would even raise a tsunami concern. It's a fair question, and it gets at something most people misunderstand about how tsunamis are born. The classic tsunami maker is a different kind of fault, one where the seafloor thrusts vertically, lifting a huge column of water and sending it racing outward. A strike-slip fault, where the ground mostly slides sideways, is far less efficient at moving water. So the textbook says a quake like this one shouldn't generate a major tsunami. But the warning centers don't bet your life on the textbook. Here's why. A magnitude 7.5 is enormous, and the rupture was shallow and close to the coast. Even a strike-slip event can shove water if there's any vertical motion at all on the fault, and on a complex rupture there usually is some. On top of that, large coastal earthquakes can trigger underwater landslides, where a slope of seafloor sediment, shaken loose, slides downhill and displaces water just as effectively as a fault would. That landslide-driven tsunami risk is real, it's happened before, and it does not care whether the fault was strike-slip or not. So the warning center did the responsible thing. It issued the advisory, watched the tide gauges and the deep ocean sensors, and waited to see what the water actually did. In the end, the water stayed calm enough. The advisory was cancelled at 12 minutes past 7 that evening, Atlantic Standard Time. No destructive wave came, and it would be easy, in hindsight, to call the warning an overreaction. It wasn't. The right way to judge a warning is not by what happened, but by what the responsible decision was with the information available in the moment. With a shallow 7.5 on a coastal fault, you warn people every single time, and you are grateful when the sea decides to spare them. That advisory is also your clearest reminder that this fault system reaches American soil. The same Caribbean tectonics that shattered the Venezuelan coast run right up under United States territory in the eastern Caribbean. Puerto Rico has its own history with large earthquakes and tsunami threats. For a few hours on June 24th, that abstract risk became a live warning on American phones. The wave almost came. Next time, on a different fault, it might not stop at almost. To understand how unusual June 24th was, you have to understand how long the warning had been building, because this was, by some measures, the strongest earthquake to strike Venezuela in around 125 years, and the events that bracket that century tell a story the country has been trying not to hear. Go back to October of 1900. A great earthquake, estimated at around magnitude 7.7, struck the same general stretch of northern Venezuela, sometimes remembered as the San Narciso earthquake. It reshaped the coastline and the historical record of the region. For more than a century afterward, nothing on that scale returned. The fault went quiet, and quiet is the most dangerous thing a fault can be, because quiet is not the same as safe. Quiet is the fault locking and loading and storing strain, exactly the way I described earlier. A century of silence on a plate boundary that moves an inch or two a year is a century of accumulating energy. But go back further, and the warning gets darker. In 1812, a catastrophic earthquake struck Caracas directly. The death toll from that disaster is often cited at around 20,000 people, though figures from 2 centuries ago carry real uncertainty, so treat that number as an estimate, not a precise count. What makes 1812 haunting isn't only the toll, it's the timing. The quake struck during Venezuela's War of Independence, and it leveled cities held by the revolutionary forces while sparing some loyalist strongholds, a coincidence that was immediately twisted into propaganda, framed as divine judgment on the rebellion. Even then, 200 years ago, people reached for a story, a meaning, a hidden hand behind the shaking, rather than face the harder truth that the ground simply moves and does not care who is standing on it. Then come closer, to 1967. An earthquake struck the Caracas area again, and this one carried a specific modern lesson. In the coastal area of Caraballeda, it was the tall buildings on soft coastal soil that suffered the worst, while structures on firmer ground fared better. If that sounds familiar, it should. It is the exact pattern we just watched repeat in 2026. The same coastline, the same soft soil, the same brutal physics of tall buildings on liquefiable ground. The lesson was written into the rubble in 1967, and the coast filled up with high-rises anyway, because that is what coastlines do. People want to live by the sea. So when officials call June 24th the worst in 125 years, understand what that phrase really means. It doesn't mean the danger appeared out of nowhere. It means the danger had been building, on a known fault, with a documented history, for longer than anyone alive can remember. The warnings were there. They were just spread across a span of time too long for a single human life to feel. There's one more piece of Venezuelan history you need, and it happened on the exact same coastline, within living memory, and it has nothing to do with earthquakes at all, at least not directly. In December of 1999, the state of Vargas, the narrow coastal strip below Caracas that includes La Guaira, was hit by one of the worst natural disasters in the country's modern history, not a quake. Days of torrential rain saturated the steep mountainsides that rise straight up behind the coast. Then the slopes gave way. Walls of mud, rock and debris, some of it the size of cars and houses, came roaring down the mountain and straight through the coastal towns and neighborhoods built at the bottom. The death toll is genuinely uncertain, with estimates ranging into the tens of thousands, because entire communities were simply buried and washed into the sea. Treat any single figure with caution. What's not uncertain is the lesson. This coast is a trap, a thin, crowded ribbon of land, pinned between a steep mountain range and the ocean, where the only flat ground to build on is the very ground most prone to failing. I bring up Vargas not to pile on dread, but because it reveals the real, recurring character of this coastline. It is geologically loaded in more than one way at once. The mountains above can come down in the rain, the ground below can liquefy in a quake, and the same dense population sits in the crosshairs of both. The 2026 earthquake didn't create that vulnerability. It exploited a vulnerability that the coast has demonstrated, in different forms, again and again. Now let me widen the lens beyond Venezuela for a moment, because the doublet itself, those two near-equal quakes 39 seconds apart, has precedents too, and they're instructive. In April of 2012, far out in the Indian Ocean off the coast of Sumatra, two of the largest strike-slip earthquakes ever recorded struck close together, a magnitude around 8.6, followed by a magnitude around 8.2. Like Venezuela, they were side-to-side ruptures rather than the vertical thrusts that usually make headlines, and like Venezuela, the first appears to have helped trigger the second through stress transfer. The 2012 event happened in the open ocean, far from any coastline, so the human toll was limited. It was a warning shot fired where almost no one lived. Venezuela was the same kind of physics, the same family of rupture, but it happened directly underneath a coastline packed with people. That's the thread tying all of this together. The fault types, the soil, the steep coast, the dense cities, none of these are unique to Venezuela. They are common ingredients, found all over the world, including under American soil. Venezuela is what happens when several of those ingredients line up in the same place at the same moment, and the unsettling truth is that the lineup isn't finished, because the fault that broke on June 24th has neighbors, and at least one of them is still locked, still loaded, and still waiting. This is the part of the story that hasn't happened yet, and it's the part the United States Geological Survey is willing to put a number on. After a major earthquake, the agency runs what's called an operational aftershock forecast. It's not a psychic prediction, it's statistics, built on more than a century of observing how earthquake sequences behave around the world. And the statistics are blunt. After a magnitude 7.5, the ground does not simply settle down and go quiet. It keeps breaking, in a long, declining series of aftershocks, for weeks and months. Most are small, some are not. For the Venezuela sequence, the forecast put the probability of a magnitude 6 or larger aftershock within 7 days of the main shock at roughly 40%. Let me say that again, because it deserves a second. Roughly a 4 in 10 chance of another major earthquake, a 6 or bigger, within a week, and a magnitude 6 is not a footnote. On its own, in a city already cracked open, with buildings already weakened, and rescue crews already working inside unstable rubble, a 6 could be devastating. That 7-day window runs to around the 1st of July. As you watch this, we may be inside it, or just past its edge. Either way, the ground has already made good on part of the forecast. More than 400 aftershocks have been logged since the doublet. The fault is not done talking. But there's a deeper concern that goes beyond the routine aftershocks, and it has to do with the fault's neighbors. The San Sebastián fault is part of a larger system that includes the El Pilar fault, and that system runs for hundreds of kilometers along northern Venezuela, eastward toward a region called the Caracas Basin. Here's why that matters. When a section of a long fault system ruptures, it transfers stress onto the adjacent sections, exactly the mechanism behind the 39-second doublet, only now playing out over a much larger distance and a much longer timescale. The June 24th rupture may have nudged neighboring segments closer to their own failure, and one of those segments, further east, has its own grim resume. The Caracas area suffered a deadly earthquake in 1997. It is a known, active, dangerous stretch of the same plate boundary. I want to be precise here, because this is exactly the kind of place where responsible science and irresponsible fear-mongering part ways. No one can tell you that the eastern segment will rupture. No one knows the day, the month, or even the year. That information does not exist, and anyone who claims it does is lying to you. What the science can honestly say is this: a major earthquake just released and redistributed enormous stress along a long, active fault system. Sections of that system are known to be capable of large quakes. The probability of significant aftershocks in the near term is high, around 40% for a 6 or larger in the first week alone, and the longer-term hazard along the rest of the boundary is real and worth watching. That's the truthful version. It's less specific than a conspiracy prediction, and far more unsettling, because uncertainty is scarier than a fake date. A fake date you can dismiss when it passes, an open-ended 40% you have to live with. And living with uncertainty is exactly what the response effort has been doing, because you cannot wait for the ground to finish before you start pulling people out of it. Which brings us to who actually showed up, and what they brought. When a city goes down, the question that follows within hours is brutally practical. Who comes to help, and what do they bring? In Venezuela's case, the answer reached across the Caribbean from the United States, and the scale of it tells you how seriously this event was taken. The United States committed $150 million in support. 2 Navy ships were directed toward the region, the USS Fort Lauderdale and the USS Billings, the kind of vessels that can carry equipment, medical capacity, and personnel to a coastline whose own ports and roads have just been wrecked. And on the ground, American urban search and rescue teams deployed, the specialized crews trained for exactly this nightmare, finding and extracting people from collapsed concrete. Teams associated with Fairfax County in Virginia, with Los Angeles County, with Miami-Dade in Florida, the same teams that respond to disasters on American soil, were sent to dig through the rubble in Caracas and La Guaira. I point to those specific teams for a reason. The crew from Fairfax County, the crew from Los Angeles County, the crew from Miami-Dade, these are your neighbors. They train in American towns, they respond to American emergencies, and when a disaster is big enough, they get on a plane and fly towards someone else's catastrophe. The line I keep coming back to in this story is the same one again. There is no clean wall between a foreign disaster and a domestic one. The same people who would dig you out of a collapsed building in Miami were, this week, digging strangers out of collapsed buildings in Caracas. There's also a hard logistical truth buried in the response, and it's one most coverage glosses over. The earthquake didn't just create victims, it destroyed the very infrastructure needed to save them. The main international airport, Simon Bolivar International, the gateway for nearly all the incoming aid, sits on that same vulnerable coastal ground in Mykatia. It was knocked out of service by the quakes. For a critical stretch of time, the front door to the disaster zone was jammed shut. It took until June 27th for crews, with American help, to get even a single runway reopened so that aid flights could land. Think about that compounding cruelty. The disaster damages the airport, which delays the aid, which costs lives, inside the very rescue window we talked about, the one that closes in 48 to 72 hours. The geography that made the coast dangerous in the first place, that thin strip of soft ground between mountain and sea, is the same geography that strangled the rescue. That is the real shape of a modern disaster. It is never just the event, it is the cascade the event sets off. And to see that cascade clearly, let's map it out, because it points straight at the question you should be asking about your own coastline. Let's lay the dominoes out in a line, because once you see them fall in order, you understand why a single earthquake can break an entire region rather than just a few buildings. Domino 1. Two near-equal quakes rupture 39 seconds apart, erasing the recovery window between them. Domino 2. The shaking is violent, but it lands on soft, water-saturated coastal soil, and that soil liquefies, turning solid ground into something that cannot hold a building. Domino 3. The tallest, heavier structures, the modern high-rises, fail first, because they concentrate the most weight onto the ground that just failed. Domino 4. The same coastal ground holds the critical infrastructure, the port, the highways, the international airport, so the disaster cripples the exact systems needed to respond to it. Domino 5. The mountains rising directly behind the coast bring a landslide hazard of their own, an orange level alert layered on top of the red liquefaction zone, the same steep slopes that buried this coast in 1999. Domino 6. The fault that broke transfers its stress onto neighboring segments, raising the odds of a major aftershock to around 40% in the first week, and keeping the longer stretch of the boundary loaded and uncertain. Every one of those dominoes is a real, documented feature of what happened in Venezuela. And here's the uncomfortable part. You can find that same row of dominoes, in different combinations, set up under American cities right now. A major strike-slip fault running near a dense coastal metropolis. The United States has that. Soft, liquefiable soil under high-value waterfront and filled land near harbors. The Bay Area has that. Coastal cities have that. Critical infrastructure, airports and ports, built on exactly that kind of vulnerable ground, because flat coastal land is where you build a port. The United States has that too, in more than one place. The specific names change. Caracas becomes a different city. The San Sebastián fault becomes a different fault. But the physics of the dominoes does not change at all. This is the part of the Venezuela story that should travel home with you. Not fear for its own sake, but recognition. The disaster wasn't a freak event that could only happen there. It was a demonstration of how a known set of hazards behaves when they line up, and it was performed on a coastline that is geologically a cousin of coastlines you may live on. The value of watching another region's catastrophe is the chance to see your own future hazard rehearsed in front of you, with the costs paid by someone else. And it's precisely because this story is so frightening and so easy to feel powerless about that it gets hijacked. Because there is an entire ecosystem online that takes an event like this and feeds you a false story about it, one that's actually more comforting than the truth. Let's take that false story apart, piece by piece. Every time the ground does something terrible, a second disaster follows online, a wave of claims that someone, or something, made it happen on purpose. So let's be clear and direct about what this earthquake was not, because the truth matters, and because the comforting lie is more dangerous than the frightening fact. This was not a weather weapon. You will find people claiming that a government facility, often the research station called HAARP up in Alaska, somehow triggered this earthquake. It did not, and it cannot. HAARP studies the ionosphere, the electrically charged upper layer of the atmosphere, using radio waves. The energy it emits is a rounding error compared to the forces inside the Earth, and radio waves directed at the sky do not, and physically cannot, unzip a fault 200 kilometers long, 10 kilometers underground. The energy released by this earthquake was the stored strain of more than a century of two tectonic plates grinding past each other. No transmitter on the surface put that energy there, and none could release it. The math isn't close. It's not even in the same universe. This was not caused by the sun. There is a popular and persistent claim, pushed hard by certain channels, that solar activity, flares and the solar wind, triggers large earthquakes. It's a seductive idea because both the sun and the earth are powerful and a little mysterious. But the science does not support it. Decades of data have been examined for a reliable link between solar storms and major earthquakes, and a convincing, predictive connection simply has not held up. The energy from a solar flare interacts with our upper atmosphere and our magnetic field. It does not reach down and pull the trigger on a fault. When you see someone tying this earthquake to a sunspot, you are watching pattern matching dressed up as science. This was not engineered, and the doublet itself is not evidence of a plot. The fact that two quakes struck 39 seconds apart feels too neat, too coordinated to some people, as if no natural process could be that precise. But we've already walked through exactly how nature does it. Stress transfer, one rupture loading the adjacent section past its breaking point. Doublets are documented all over the world, including that pair in the Indian Ocean in 2012. The timing isn't a signature of human design, it's a signature of physics, the same physics, every time. And this is not the beginning of the whole Caribbean plate, suddenly letting go in some chain reaction apocalypse. Yes, the rupture transferred stress to neighboring segments. Yes, that raises real, near-term aftershock odds. And yes, the eastern part of the boundary is worth watching. But a single earthquake, even a great one, does not cause an entire plate boundary to unzip in days. Faults rupture in segments, over timescales of years to centuries. The honest hazard is serious enough without inflating it into a doomsday script. So here's the truth, and I want to land it plainly. No one fired a weapon. No one is in control. The sun did not reach down and shake Venezuela. There was no hidden hand, no plan, no purpose. And that is the genuinely unsettling part, far more than any conspiracy. Because a weapon can be switched off, a plot can be exposed and stopped, but a fault that has been quietly loading for 125 years answers to no one. It does not warn you, it does not negotiate, and it does not care. The truth is more frightening than the conspiracy, precisely because there's no villain to blame and no off switch to find. There is only the ground, and the physics, and the choices we make about where and how we build on top of them. Let me bring this back to where we started. 39 seconds, 2 hammer blows, and a promise I made you at the beginning that the strongest shaking on the map would not turn out to be the thing that did the most killing. Now you know why. The violence of the shaking mattered, but it was the ground itself that decided who lived and who didn't. The soft, saturated coastal soil that liquefied, that turned to something like quicksand for a few seconds and pulled the tallest towers down into it. That is the hidden mechanism behind the worst of the collapses. The earthquake was the trigger, the liquefied coast was the weapon. And the coastline that failed in 2026 is the same one that failed in 1967, the same one buried by mud in 1999, a thin strip of crowded, vulnerable land that keeps demonstrating its danger to a population that keeps having no choice but to live there. And here's the open question I'll leave you with, because the story is not finished. The thing that is still moving, tonight, is the fault. More than 400 aftershocks and counting. A roughly 40% chance of a major one, a 6 or larger, in the days right after the main shock. A neighboring stretch of the boundary, out toward Caracas, that just had stress loaded onto it and has its own deadly history. None of that is a prediction of doom. It's an honest description of a fault system in motion, refusing to settle, while a wounded region tries to dig out from the first blow. We don't know what it does next. We only know it isn't done. If you take one practical thing from all of this, let it be this. The hazard under a city is not just the fault, it's the ground. If you live somewhere with seismic risk, the soil beneath your building matters as much as the distance to the nearest fault line, and that's a question worth asking before you ever feel the first tremor. Knowing what you're standing on is not fear, it's the opposite of fear. It's the one piece of this that you can actually do something about. Here at the Horizon Lab, that's the whole point. The real data, the honest uncertainty, the science underneath the headline, because you deserve better than to be scared by people who won't show you their sources. And if the ground itself unsettles you, then there's another place on this planet where the Earth is moving right now, except this time you can watch it happen, on camera, in real time. There's a volcano in Hawaii that has erupted nearly 50 separate times in a single ongoing sequence, and scientists have gotten so good at reading it that they can now forecast its next eruption within a window of days, sometimes calling the date almost exactly. How do you predict the unpredictable? That's the question waiting in the next one. I'll see you there.